AP Chemistry. We are in Unit 2 Reactions, and this is Lesson 2 on Chemical Equations. So what have we learned so far in Foundations? You learned how an atom is structured and periodic trends of the periodic table across, and that helps you to understand chemical bonds, the three types of covalent, ionic, and metallic bonds. And those create compounds, either molecules or compounds, two or more elements. Now we're going to start putting those compounds into what's kind of like a sentence of chemistry. It's the chemistry equivalent of a sentence, and that's called a chemical equation. And just as a sentence is really the centerpiece of a language, a chemical equation is the centerpiece of chemistry. So we're going to see how a chemical equation is written. So chemical equations are the centerpiece of the study of chemistry. Chemical equations are a recipe that shows how reactants recombine into new substances called products. The one-way arrow indicates that the reaction moves from left to right and not backwards from right to left. So when you write a chemical equation like this, the reactants are on the left. That's what you're putting into the beaker or container, and what's going to come out, the products, are on the right. So the way this is read is, one way to read this is 1 molecule of methane, CH4, plus 2 molecules of oxygen. The G stand for gas. The state of matter here is gas. Is going to produce 1 molecule of carbon dioxide, CO2 gas, and 2 molecules of H2O. Now the H2O could be a gas, but in this case that's an L. It's kind of a scripted L, and it means liquid. Here are 3 ways to interpret a chemical equation. 1 molecule of CH4 and 2 molecules of O2 combine to produce 1 molecule of CO2 and 2 molecules of H2O. So there you see what are called particulate diagrams of those molecules, and that's one way to think of this. It's just an individual number of molecules, and that's the key to chemical equations. They deal in numbers of molecules, numbers of atoms, numbers of moles. They don't deal in masses such as grams, and that's going to be an important concept coming up here soon. We must always convert things into a number of particles, usually in moles, in order to get the chemical equation to work for us, to interpret what's going on. Or we can view the equation in terms of moles. So here's the same equation. So 1 mole of CH4, so that's one of those big baskets of 6.02 times 10 to the 23rd molecules or atoms or particles. In this case, they're methane molecules. And we have this very large number so that we can see them and actually weigh them on a scale. So we're taking one of those big baskets. Each basket represents 6.022 times 10 to the 23rd molecules. And then we're going to take 2 moles of oxygen. So that's 2 times 6.022 times 10 to the 23rd. So we're simply scaling everything up from individual molecules up to moles, big baskets of molecules. So what we're going to end up with is one big basket, 1 mole, 6.022 times 10 to the 23rd of carbon dioxide, and 2 of the big baskets of water molecules, 2 times 6.022 times 10 to the 23rd. Again, we prefer to work with these big baskets because we can actually see them and weigh them on a scale. But notice the relationships are the same. And so we're going to talk about really the way that you should interpret a chemical equation. It's not purely as number of molecules or number of moles, but it's in this way. Or we can view the equation in terms of ratios. So there's the same equation. So whatever number of moles of CH4 reacts, twice as many moles of O2 are needed. So in other words, we're not saying we have necessarily exactly 1 mole of CH4 and exactly 2 moles of O2 here in this example. If that were the case, it wouldn't be a very useful equation. If you always had to have exactly 1 mole of CH4 and exactly 2 moles of O2. A better way to think of it is, however many moles of CH4 you have, you need twice that many moles of O2. So if, for example, we have 1.3 moles of CH4, we're going to need twice that many, 2.6 moles of O2. If we have 50 moles of CH4, we're going to need twice that many, 100 moles of O2. So rather than thinking of it as a specific number of molecules or a specific number of moles, think of it as a relationship. That in this case we need twice as much O2 as the amount of CH4 in order to make this reaction work. So this requires a ratio of 2 moles of O2 for every 1 mole of CH4, whatever those numbers are. And over on the right side, you're going to have 1 times the number of moles of carbon dioxide, CO2, and 2 times the number of moles of H2O. So let's go back to the example. If we did have 1.3 moles of CH4, we would need twice that many, 2.6 moles of O2. And what that would produce, notice that there's a 1 in front of CO2 and a 1 in front of CH4, so it's a 1-to-1 relationship. So if we had 1.3 moles of CH4, we would end up with 1.3 moles of CO2 and twice that many moles of water, 2.6 moles. So just think of it as its relationships. 2 times as many oxygens as CH4, 2 times as many waters as CO2, the same number of CO2 as CH4, the same number of H2O as O2. That's the way to think of it, is just ratios or relationships. Particulate diagrams provide a simple picture of the motion of atoms and molecules in a chemical reaction. The way that chemical compounds break apart and recombine will be covered later in that course. That's really a part of the subject of chemistry called kinetics. Particulate diagrams show a beginning and final diagram of a reaction. It might also show an intermediate state of the reactants. So there you see that the CH4 and the O2s broke apart into individual atoms. How did they do that? Simply by smashing together. Now that's easier said than done, and as I say, it's more complicated than that when you really study it. That's called a reaction mechanism, and we'll study that later in the course. But basically they break apart. And then what they then do is they recombine to form the product. So now you have 1 CO2 and 2 water molecules on the right. Okay, and we're going to call that a 3-stage particulate diagram. It's called a particulate diagram. I just added the term 3-stage to indicate you show the reactants, you show them broken apart in the middle, and then you show the products at the end. Now, why wouldn't they go from here, instead of going forward, back to here? They smashed apart. Why wouldn't they put themselves together again the way they were originally? They could do that. They need a certain amount of energy to break apart. However, the short answer is, and we'll go into this in more detail later, is that these atoms are combined at a lower energy state in this configuration, 1 carbon dioxide and 2 waters, than they were on the reactant side, over on the left side. They're at lower energy. Everything in nature wants to go from higher to lower energy. That's just natural. Just like you drop a pencil, it goes down to a lower energy level. Okay, so that's in short why this is happening. But you don't need to understand that. Just understand what the particulate diagram is and what it's showing. It's just a picture, an illustration of what's going on in the chemical reaction. Conservation of mass. Antoine Lavoisier, known as the father of chemistry, developed the idea of conservation of mass in the late 1700s. Conservation of mass means that the mass of the reactants before a chemical reaction must equal the mass of the products after the reaction. In short, what that means is you cannot create or destroy atoms. Whatever atoms you had before the reaction, you must have those same atoms at the end of the reaction. So for example, this means that if you bulldozed and burned Hoover High School to the ground, the mass of the rubble and smoke would be exactly equal to the mass of the school before it was destroyed. If you could capture all the smoke, they would be exactly equal. You have not lost or created any mass. What this really means for us, and what we're going to do in the next couple of slides, this means that the number of atoms of each element in the products, that's at the end of the reaction, must equal the number of atoms of each element in the reactants. That's before the reaction. They have to be equal numbers of atoms before and after. And that's going to guide us as we learn how to balance equations and why we need to do that. So, there's two methods for balancing equations. The easier of the two, and the one that's easiest to learn, is called the box method. So an equation must be balanced before it can be used in chemistry. The first method is called the box method. This is a good method for beginners. You eventually want to move past this. It takes a lot of time to do it, relatively a lot of time to do it, and a lot of space on your paper. So let's just take a look. There's a chemical reaction. So what you'll notice, among other things, is that on the left side, on the reactant side, the left side of the arrow, you have two V atoms. On the right side, you only have one V atom. On the left side of the arrow, you have one H, hydrogen atom. On the right side, you have two. Well, you can't have that happen. You can't have atoms being created or destroyed. You have to have the same number of V before as after, and the same number of H, and the same number of O, and same number of Cl. So they have to be equal on both sides. So what balancing does is it gets us to that situation where you have equal numbers of V's on both sides, equal numbers of O's on both sides, equal numbers of H's on both sides, and equal numbers of Cl's on both sides. Okay? There are different orders in which you can balance an equation usually. So the order in which I'm doing things does not have to be the only way that you do them. But what you do is this. You take the chemical formula for each compound and you break it into individual atoms. So we have two V atoms on the left and 5 oxygen atoms on the left as well in that first compound. V is vanadium, by the way. Then for HCl, that's hydrochloric acid, you have one H atom and one Cl. Remember, if there's no subscript, no little number down there, it means it's 1. Then you go over to the right side of the arrow, you have one V, one O, and 3 chlorines, 3 Cls. And finally for the water, you have 2 H's and 1 O. So what you do is you pick one of them and you balance it first. Now what you want to stay away from is any element that appears more than once on the same side of the arrow. So in this case, oxygen appears in 2 different locations over on the right side. It appears in VOCl3 and it appears in H2O, so stay away from that. It's going to be complicated to balance. You want to save that for the end. The other thing you stay away from is a pure element, either an atom or a molecule like O2 or H2 by itself. You want to stay away from those because they don't help you balance anything else. You'll understand that concept as you gain some experience. So here we go. We're going to go ahead and we're going to start with the V's. We have 2 on the left. We only have 1 on the right side of the arrow, so we're going to add another V on the right side. But in doing that, you have to add everything else that's in that compound. So we not only added 1 more V, we added 1 more O, and you had to add 3 more of the Cl's. In other words, you have to add an entire box, not just one element that you want to increase. So now if you look at it, we have 2V on the left and 2V on the right. So now we have V in balance, so we're going to move on to something else. Well, we said we're going to stay away from O because it appears in 2 different locations on the right side. So we're going to stay away from that. So what we're going to do next is we're going to go over to Cl. We have 3 Cl's on the right, 6 Cl's on the right. Cl, 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 and the second box Cl, Cl, Cl. You have 6. So you need 6 of them on the left. So we're going to have to draw 6 of these HCl boxes. 5, 6. So now we have 6 Cl on the left and 6 Cl on the right. We haven't changed the number of V. There's 2 on the left, 2 on the right. So we now have V in balance and we have Cl in balance. What we've done though is we've vastly increased the number of hydrogens. H, we have 6 on the left and only 2 over on the right where the water is. So what we need to do is add 2 more water molecules. So HO, HHO, HHO. So now everything is in balance except oxygen. Maybe it is, but we don't know. We have 2V on the left, 2V on the right. We have 6Cl on the left, 6Cl on the right. And we have 6H on the left, 6H on the right. Now let's count the oxygen and see how many we have. Well, over on the left we have the O5, so that's the V in the VO5, so there's 5 oxygen on the left side of the arrow. And on the right we have 2 of them in the VOCl3, and we have 3 more in the water, so we actually have 5 on the right side as well. So the oxygen are also in balance. That will often happen if you leave the complicated one, the oxygen in this case, to the very end. It will end up balancing out anyway. So we now have a balanced equation. So the way you now write this is you write the number of boxes as coefficients in front of each compound. So V2O5, there's 1 box, so it's 1 V2O5. You don't have to write a coefficient of 1, but I recommend you do it, and I strongly recommend you do it. Then you have the HCl, you have 6 of those boxes, so it's 6 HCl. And then over on the right, you have 2 boxes of EOCl3, and then you have 3 water molecules, 3 H2O. So that is a balanced equation. You have the same number of atoms of hydrogen on both sides, the same number of oxygen on both sides, same number of chlorine on both sides, same number of vanadium on both sides. So you balance this equation. You can only use a chemical equation when it's balanced. You cannot use in chemistry an unbalanced chemical equation. So you need to become good at this skill. Now we're going to use a little more sophisticated method. It's the way I'd like you to learn to do it. It's just by counting atoms on both sides. This will seem a little harder at first. The box method will seem easier. But the box method, as you saw, takes up a lot of space and takes a lot of time to write out all the boxes. So you should eventually learn to do it this way. And it's just really by counting atoms. So the second method is a standard way to balance the chemical equations. Okay, so what do we have? Well, we're going to kind of do it the same way we did with the box method. So first we're going to count the atoms we have on each side. So for vanadium, we have 2 on the left and 1 on the right. For oxygen, we have 5 on the left and 2 on the right, 1 in VOCl3 and 1 in H2O. For hydrogen, we have 1 on the left and 2 on the right. And for chlorine, we have 1 on the left and 3 on the right. So nothing's in balance. So again, you want to stay away from oxygen. You can pick any of the other 3 that you want. We're going to go for the vanadium just like we did with the box method. So we're going to put a 2 up there. The reason we put it up there, it should go right in front, but we don't know that that's going to be the final coefficient. The numbers in front are called coefficients. We don't know that's going to be the final one. We may need to change that again. So I have students write that up above. So now what do we have? We have 2 V's. So now we change on the right side that V to a 2. But we also, that 2 distributes through to everything else in that chemical compound formula. So we now also have 2 oxygens there in the VOCl3. But there's also the oxygen in water, H2O. So you have 2 O's in the VOCl3 plus 1 more in the H2O. That means you now have 3 oxygen. So we're going to cross the 2 out and put a 3. Then you finally distribute that 2 to the Cl3. So it's 3 atoms of chlorine in that for each molecule, and you have 2 molecules. So now you have a total of 6 atoms of chlorine. Remember, you're counting atoms, not molecules here, individual atoms. So there, we've totally taken care of that, and we've changed that. So what we have now is the V is in balance. Okay, now we're next going to go to the Cl. So we're going to put 6 in front of HCl. In order to have 6 Cls, we have to put the 6 in front of everything. So now we have 6 hydrogen and 6 Cl over on the left. So we're first going to change the hydrogen. There's 6 hydrogen. And now we're going to change the Cl. There's 6 Cl. So now the chlorines are in balance. You have 6 on both sides. The vanadiums stayed in balance. Sometimes when you put a second element or a third element in balance, you'll throw one of the earlier ones out of balance temporarily, but eventually you'll get it back in balance. Okay, next up. So we want to now balance the hydrogen. So we're going to put a 3 up above the H2O. So now we have 3 times H2, that equals 6 hydrogen atoms. So we're going to change that to 6. But we also have now 3 oxygen there. So what that means is for oxygen, we now have 2 in the VOCl3 and 3 more in the H2O. That's a total of 5 oxygen atoms. So we're going to change that 3 to a 5. And now we look at that, everything is in balance. The V, the O, the H, and the Cl are all in balance. So we're going to go ahead and write those coefficients in front permanently. So it's the same exact equation you got in the last slide, you just did it a different way. Okay? But you have the same number of atoms of each of those elements on the left as you have on the right. You have to have that, otherwise you can't use the chemical equation. And that takes care of the lesson on balancing equations. So you want to practice this. We'll do a lot of this and practice this a lot. You have to be really good at this because, as I say, you can only use that equation if it is in balance. So that takes care of that, and we'll see you on the next lesson.